The punchline is that most of the weights in a model actually really aren't that important. So this is the sparse weight problem. That really a small percentage of the weights contribute to the majority of the actual functionality. Right. And so this kind of sort of backs up that idea because if you can use one bit, and this is 1.58 bits, negative 1, 0, and 1, means that the level of precision you need at each weight actually isn't really required. You can overcome that by just having more blocks.
Okay.
And so they tried that and it worked.
Welcome to Practical AI, everybody. My name is Jeff. I'm here with Peter Lin. Practical AI is brought to you by Pocket AI. Pocket AI is a tool that you can use to increase accuracy in your models without additional training or data and prune up to 60% of the weights in your data without loss. Peter, today we want to hit up this Microsoft thing, but before we get there, Nvidia made an investment in Intel. What
Yeah.
is going on there?
Apparently they purchased 4% of Intel. It looks like it was at a fixed price. So I don't know the details of it, but it's 5 billion. It's supposed to be 4%. So they're the third largest stakeholder. The other ones are actually funds. Um, my guess, I have no proof or evidence, but my guess is the government said, "Hey, look, you need to help Intel, so do this for us." And so,
You think this is just a favor?
yeah, I think so.
No, but they're going to use a bunch of Intel chips for something, right? I mean, it's
Right.
probably like maybe not they're not using 5 billion worth, but do you
Yeah.
think that some of this just is like, look, we're buying a bunch of stuff anyway. Let's just own some of the company.
I think it's mostly just kind of as a backup and just to play nice with the government. Um, Given the current government is doing some weird ass stuff like owning shares of Intel.
Yeah, even though they're
Yeah.
saying the Trump administration had no involvement in this
Yeah,
partnership.
right.
Okay.
Yeah, I mean, like, so the GPUs will still be manufactured by TSMC. The ARM CPUs will also be by TSMC. So the other stuff, the networking chips, and maybe like all the other chips that they need, they could, in theory, have Intel as a second source.
Okay. So like the stuff in their data centers and stuff like that, this
Yeah.
could come in handy. Okay.
Yeah, but the downside is even if Intel fabs it, you can't assemble the stuff in the US. It's all shipped to Taiwan and China anyways to assemble,
Okay.
which is the ironic part.
Good. Well, let's move on to a more interesting story. The Microsoft thing that kind of had, I think you said at one point this was a paper that came out, but essentially they've got a model that can run on your laptop that's pretty good.
Yeah, yep, it's a 1 bit. And basically, this paper came out last year from Stanford where they experimented with using 1 bit for the actual training in the model instead of floating point 16.
Okay.
And there's also the brain float 16, which is a variation that's tailor specific for machine learning. And they found that hey, it actually kind of works, which is nice.
Well, so this is on the image here I've got, or on the screen here I've got from the YouTube that we'll link. Um, that essentially a bit, if I understand correctly, uses 16 or sorry, a weight uses 16 bits, and that's because the number is essentially anywhere from, I mean, not really, but -1 to +1, something like that, right?
Yeah.
It's
Hmm.
basically like a probability that the calculation is going to come out there. And what they did was they basically shrunk it down to
Yep. Negative one,
everything.
0, 1.
Yeah, everything can be a one or a zero or a one, right?
Yep.
And so it's a little over a single bit
Yeah.
per.
1.58 bits.
But just looking at this one versus the original, the way it actually works,
Hmm.
how could a model train if it's if it's only going one to, I mean, it goes from like infinite possibilities basically to three.
Yeah. So the the punchline is that most of the weights in a model actually really aren't that important. So this is the sparse weight problem. That really a small percentage of the weights contribute to the majority of the actual functionality. Right. And so this kind of sort of backs up that idea because if you can use one bit, and this is 1.58 bits, negative 1, 0, and 1, means that the level of precision you need at each weight actually isn't really required. You can overcome that by just having more blocks.
Okay.
And so they tried that and it worked.
But maybe it makes sense that the sparse weight problem could be, that you could take advantage of the sparse weight problem with this. But wouldn't it mean that, couldn't I argue if I didn't know that this worked? Couldn't I talk myself out of this idea by saying, well, right, but the weights that do work, that do matter, they do need an infinite range to train on or to figure out. They're not just going to be positive or negative or zero. They
Right.
need an infinite value.
Yeah. Right. And so if you go back to kind of biology and neuroscience, human brains are analogs. Our signals aren't zeros and ones, they're these analog waves. And so when neural networks were first created, way back in the 60s and 70s, they thought, well, okay, let's try to capture that with these floating point precision numbers. Try to simulate what a wave looks like.
And that's what we end up with, sort of a digital binary whatever.
Yep. And then so now because we realize, oh, okay, these huge models are trillion parameters, and so how do we crunch it down so it's 10 times smaller? Well, instead of 16 bits, you do 1.5, so it's 10 times less.
Okay, so do these work? These models?
So the early result shows that it's good for basic stuff, but it's bad for programming and reasoning.
Okay. And reasoning, has its own, set of trapdoors in terms of
Yeah.
definitions. But why would it struggle with sort of calculations? Why would it struggle with?
Well, it struggles with reasoning because there's more subtleties. If it's just ones and zeros, you don't have the range of things you can capture, basically.
So can
So,
it do math but not programming?
no, it's good at like summarizing English type stuff.
Okay.
But things that actually require logic and reasoning, like math and science and programming, apparently it does terrible.
Wouldn't it make sense to like reverse engineer this and say, okay, let's try to train models using this thing. Okay, great. Now we know what weights matter and which ones don't. Now let's turn those into 16-bit weights and get some sharper refinement.
Unfortunately, no, because the way the chips work is they all have to be the same type of numbers. So in other words, if you have like an attention layer or a fully connected layer, all those values have to be the same type. You can't mix it. You can't mix a 1 bit and a 16 bit and have it all be this matrix, this 2D grid, basically.
Could
Right.
you could you strip it out and say these are the only weights that matter? Let's now remove all the other weights and just train on a new platform with just 16-bit weights in that place, or is it not that
Unfortunately,
easy?
that doesn't work because once you've done that, you're basically starting training from scratch anyways.
So where will this go? Where will this one-bit architecture go?
It'll be interesting. We'll see where it goes. I mean, no one knows. I mean, I don't know. But it's good to see that you can use a 1 bit a 1 bit number instead of a floating point. So you save on memory, you save on bandwidth, you save on latency, you save on power, all the usual things with having less memory, less bandwidth, less compute, less I/O. So it's all good. But the real question is that what can we learn from this to evolve to the next two levels of architecture? That to me is the interesting part. It's not like this is a nice window into what might be possible, but until we learn more from it, we won't know the ultimate.
I don't get the sense that you think this is as profound as DeepSeek hitting the market.
No, it's not. No, it's a really neat trick to reduce the size of a model.
But that's it.
Yeah.
Okay. All right. That's fair enough then. All right. Well, remember you can follow us on Spotify. So find us there if you like the audio version of what we do. Share any questions or thoughts. We'll look for new topics, and we'll be here next week. Thanks, everybody.